We have seen many talks on information set decoding. Now we have to redefine ISD, which is now integer syndrome decoding. And the talk will be given by Pierre-Louis Cayrel. And
hello?
Hello?
You can hear me?
Yes.
Great. So I can start, or I didn't really heard you?
Yes, you can start.
Okay. So thank you, Eduardo. Thank you, the organizers, for your great job for the last 2 days. It's a chance for me to be the last speaker. So see that I'm the last. I have removed most of my first slides because you already know many things already about code-based crypto. So I will directly go to the foundation of our work. So I am Pierre-Louis Cayrel, and I will present you a joint work I've done with Vincent Grosso, who is my colleague in Saint-Etienne. I also work with Brice Colombier from Grenoble and Vlad Dragoy, who is from Romania. So the syndrome decoding problem, you all heard about it in the last 2 days. So I will just give you a brief recall of what it is and why it's hard to solve, and why I won't try to solve it, but I will try to solve an easier problem. So if you all remember, the binary syndrome decoding problem is defined as following. You have a matrix H, which is of rank n minus k over F2. The code has length n, so you have a matrix of size n minus k times n over F2. You have a vector S star, which is composed of n minus k values in F2 and a value t, which is a positive integer. And the question is to find a vector x, which has a weight lower than t, such that the XOR of t column of H is equal to x star. I say XOR because it's a multiplication of H and X, but in F2. So it's really important to understand that in this context, we are doing the XOR of only t column of H to obtain the syndrome S star. So you all know that this problem is NP-hard. It has been studied a lot. And I will not work on this problem. I will work on a different one. I will study the N-SDP problem, where n means that the syndrome entry is in n. All the coordinates are integers. So you have a matrix H, which is also binary, but I will not see it as a binary matrix, but just a matrix with elements which are 0 or 1s. A vector S, which is an element of n to the n minus k. And we always have this t value, which is the Hamming weight, which means the number of non-zero values of a vector x of 0, 1 to the n. So it's not really F2, it's just a vector which has value either 0 or 1. And when I compute the product H times X, in this case, I do the sum, the addition of t columns of H. And I obtain the syndrome S, which has values in n between 0 and t. So it seems obvious that this new problem is easier to solve, because when you have S, you have more information than we add in the binary SDP, because if S is equal to t, we can remove the column of H, which have a 0 on this position. So it's clearly an easier problem. And in this presentation, I will show you how easy it is, and I will detail an algorithm to solve it. And then I will conclude. So, okay, it's an easier problem, but is it realistic to study it, or it's just a fantasy? In fact, this problem can be derived from the binary syndrome decoding problem using either fault injection. So it's what we have done in our Eurocrypt last year paper. Using fault injection, we were able to change an XOR into an add. So when we were computing the encryption of a message, instead of doing the XOR of t colon of H, we succeeded to flip a bit during the instructions, and the XOR became an add. So in this case, we were able to go from the binary SDP to the NSDP. We can also have this knowledge of the value of the syndrome in N using the side channel analysis or side channel informations, like we did in a recent paper which we posted on Imprint in 2022. You have the reference in the bottom of the slide. And in this case, we also succeeded to find the value of the syndrome in N, but we didn't need to use a fault injection. We just analyze the power consumption. So the motivations are, we can have the value of the syndrome in N. If we analyze this properly, the execution of the encryption step in a classic MAC list, for instance. So it's something really which makes sense. It's not a weird problem. It's really a problem that we can obtain by doing a side channel analysis properly. But when we do side channel, we have a problem. It's that the exact value of the integer is not always found. For instance, instead of having the value s in n, we will have the value with an extra noise. So it's what we will study here. We have the same case as before in the NSDP, but instead of having the syndrome S, we add a noise, epsilon, which is a discrete probability distribution of noise. But like in MAC-Ellis cryptosystem, for instance, we also have access to the ciphertext, and the ciphertext is a vector F2. So we have access to S, which is a ciphertext, which has been computed properly, but we also have access to a value of the syndrome in N with some noise. You understand? We have this S plus epsilon, which is a syndrome with some noise, and we have the value of S star, which is the correct value of the syndrome mode 2. And the goal of what we will do today in this presentation is to find the correct vector X of weight T. So the sum or the addition or the add of T colon of H, which give us this correct S star with the knowledge of S tilde, which is the syndrome in N plus noise. So we will try to solve this. Okay, so how can we solve it? In fact, it's a problem which has been studied in another context. So you can find the paper in archive, which is called the quantitative group testing. We combine some ideas from this paper with the very famous that you all know now, the information set decoding algorithm. And combining those two techniques, we succeeded to solve the problem. The main idea here will be to assign a score to each column of the parity check matrix. Because what we want, it's the column which were involved in the matrix vector product. We want to know what are the columns summed to obtain the corresponding syndrome. So for each column, I will show you how we will do it. We will assign a score, and with this score, we will be able to select the correct columns. We want to distinguish the columns which are in the support of the solution from the columns which are not involved in the product, so which are out of the support. So the score is described as follows. I will give you a third example in the next slides, but the main idea will be to consider this is a column of H. This is a noisy syndrome we obtain. So we compute the scalar product between those two, and to consider also the values which are 0. We use another matrix, which is 1 minus H. We flip all the bits, the ones become zeros and 0 become ones, and we multiply it by T minus SL to have a value for the 0 entries. So here is my example. Let's assume that H is a public key. So you have this matrix of elements in 0, 1. You have 4 rows and 9 columns. And you know that we sum 3 of those columns to obtain 1, 3, 2, 2. I consider the case where we have no noise. So the goal will be to to find which are the columns of H whose sums give this S. To attribute a correct score, I need to introduce another matrix, which is 1 minus H, so which is a complementary matrix. So I flip all the bits. And here, to consider another syndrome, I use the T minus S tilde syndrome, which is the complementary to T of this S tilde syndrome. So for the first coordinate, it's 3 minus 1, 2, 3 minus 3, 0, 3 minus 2, 1, and so on. So now that I have those two matrices and those two syndrome vectors, I will compute the score for each column. So I will give you a detail for the first column. For the first column, we take the first column of the matrix H that we multiply by the syndrome S tilde, 1, 3, 2, 2. So we do the dot product, the scalar product between those two vectors. So this gives us a value. So 3, 5, 7. And we use the second matrix, the 1 minus H matrix, and we do the same. We take the first column, we multiply by this vector, and we obtain 1 times 2, which is equal to 2, 0, and so on. So it gives us a weight of 9, which is the score of this first column. And we do so for all the other columns of the matrix. So we obtain different scores, which is 9, 7, 6, and so on and so forth. With these scores, we can sort this psi in descending order. So we take the highest score, which is 9 here, then 8, then 7, and so on. And this order will give us the score of the columns, which will tell us that if we take column 1, 9, and 2 here, 1, 9, and 2, it works perfectly. It gives us the correct syndrome. So we had just to add the 3 columns to obtain the solution. Okay, but we have been lucky. We have been lucky because it's directly the first 3 columns. If it's not the case, if our score is not able to distinguish so properly the columns of the matrix, we can do a different strategy. So what we want to find the column which are involved in the product. So if we derive a column permutation from the score by sorting the indexes in decreasing order with respect to the score, we find a good permutation of the columns with respect to the information set decoding algorithm. Because in the information set decoding algorithm, as you already heard during the last days, we need to find first a permutation of the columns, then we do a Gaussian elimination like transformation, and our score here is given the good permutation. When we have this good permutation, we just do linear algebra, Gaussian transformation, and we directly obtain the result. We use the name of branch because we don't need very fancy improvements of the information set decoding. We just need a branch-like decoder, but we could also use techniques like Librical and all the new variants. But the idea is always the same. We will do our information set decoding, but in the first step, instead of taking randomly the permutations, we will take the permutation from the list Ci of the score, Ci of S. When we have done this, we do the steps 2 to 5 are exactly like in the classic ISD. It's straightforward. So it's very fast. We just have to compute matrix vector product. We just have to sum some columns. If we don't find the T correct columns in the T first places, it's fine. We can find them in the first n minus k highest scores, because we need to find a correct set of T columns out of n minus k. So if we have in the first part of the matrix the T columns which are involved in the score, it's fine. And we can also find the T columns in the n minus k first, except maybe 3 columns that we lost and which are on the right part. Using the ISD, you can be okay only if the scores are in the n minus k minus 3 first positions. We implemented it and we obtained several experimental results. So first of all, we start in the noiseless setting, so which means that we have a perfect integer syndrome. So we have the value of the syndrome in n. All the computation were done properly. We analyze this using side channel and obtain the correct results. And we have an algorithm which has the following features. So if we fix the value of n, which is the length of the code, for a fixed t, the probability of success increases with n minus k, except as more information is added when n minus k increases. I will show you this in the next graph. And for fixed n minus k, the probability of success decreases when t increases. So we have the ratio of syndrome entries considered, because in this case, we don't need to have all the rows of the matrices. We just need a smaller ratio, like for the red line, only 62% of the rows of the matrix to have a score which leads us to a number of ones in the first n minus k positions, which implies that the information set decoding algorithm will succeed. So only with 62 of the entries of the vector in n is enough to find the correct vector x of weight t, which satisfies h times s equal to s. So to find the solution of the syndrome decoding problem. So which is quite nice, because we don't even need the full system of equation of the full matrix. We just need a smaller percentage of those entries. Only 62 entries is enough for parameters. The parameters I show you here are the classic Michaelis sets of parameters. And we see that when the security increase, the number of rows needed, so the ratio of syndrome entries needed is also increasing, so which makes sense. So it's great interest of the context of side channel analysis, because when we do side channel analysis, we have noise, we have perturbations during the process, so we will not be sure that all the entries we have collected are correct. So to require less than all the entries is a plus. But when we have a noisy syndrome, how does it work? If instead of having S tilde, we have S tilde plus epsilon, which is a noise, does our score function is still efficient or not? What I will show you in the next slide. So to do so, I will generate random vectors epsilon following a binomial distribution centered around 0. So I add a noise, which is following this binomial distribution. And I try to successfully find the correct vector x, even if my syndrome is not correct, but noisy. For each matrix, we computed the number of ones in the first n minus k positions, which means that we will try to find the scores of the correct columns in the n minus k first positions. So here, what we obtain, we have a different level of noise. So either we have a small noise, which is T over 4, with our binomial T over 4 and 1/2. We have the purple line, which is here. The red line is the green line, sorry, the green line is a line for which we succeed in finding the solution of the problem, because we have a delta, which is equal to 3 here. And even if we are missing 3 columns, we succeed with the information set decoding. So the noise is centered around 0 and symmetric, and the score decoder tolerates it. So we did it experimentally, and it works. So even if the acquisition is not perfect, if we have some noise on the syndrome value, that's fine. We can still succeed to find the correct vector X. So this is the object of another new paper that we have posted on ePrint last week with all my colleagues. So we have a more theoretical results about this results, which is just experimental on the slides, but we have more theoretical results. So that's why that was for classic Michaelis, but we can also investigate the bike candidates. So for bike candidates, it's even more successful because we need very few syndrome entries because the parameters are slightly different. They are much bigger. So even with a few entries in N, we can successfully recover the correct X. We can solve it very efficiently in this case. So that's conclude my talk. Thank you very much for your attention. If you have any question, I will be happy to answer you.
Thank you for your talk. You showed in the experimental results, was it only considering that in the first n minus k minus delta spots you find all of the error coordinates? Because you could also extend your algorithm by sampling from the first n minus k plus something and then like trying all the sets or something to increase the probability, right?
I think I understood your question. So we just focus on the n minus k minus delta first positions because our results were already so successful that we didn't try to use more sophisticated techniques of information set decoding. We just use a branch, so the first idea of the ISD, and it was already enough to have a very high result of success. So if we want to investigate a bit more, maybe we can go into more details on this value delta here, which give us a success. But this might be in the next work.
Okay. But I'm not referring to more advanced ISD algorithms, but just the fact that you could like sample from the first n minus k plus something entries and choose information set from there. So this would be a very easy extension of analyzing.
So I think I didn't get your question. Sorry.
Okay, I think it's answered. Thank you.
Sorry.
We have a question here from Jean-Christophe.
Yes, thank you very much, Pierre-Louis, for your talk. I had a simple, quick question regarding HQC. Did you try to apply similar techniques, similar work to HQC as you did for bike, for instance?
No, we didn't. So far, we just focus on developing the algorithms. So we try to improve the efficiency by reducing the number of rows, but trying to on HQC, we would try to think about the structure, which is a quasi-cyclic structure underneath under the underlying structure, but we just focus on random matrices. We even for Michaelis, we didn't try it on GOPA hidden GOPA codes. We just attack a random matrix of size with the parameters which are on the paper. But it's probably something that we can do in the future. So using the structure, the underlying structure of the code, like the quasi-cyclicity, as you said, to improve even more the algorithm. But so far, we didn't do it.
Okay, and similar results would also apply to bike, I guess, with the quasi-cyclic structure.
Yeah, so we just do on the parameters. We don't use the structure of the code so far.
Okay, thank you very much, Pierre-Louis, again.
You're welcome.
You mentioned that you implemented Canvas for decoder, and in your papers, are you giving some link for GitHub link for people to download to verify to check?
Sorry. I heard you talk about Librical maybe or something like this. Maybe you should
The question was if your implementation is open source, is it available on GitHub?
I think so.
Okay. So there will be a link in the paper.
Yes.
Okay,
perfect.
perfect.
Probably
That's very good.
Otherwise, you can send me an email and we can collaborate if you want.
Okay, perfect. I think I think from the talk it gives the impression that your tech is way more successful on bike, but I think it's giving the wrong impression, right? Because the ratio there, I think if you take it in absolute values, then probably you need for Macalise you need more information than for bike, right?
Yes. So because the parameters of bike are much bigger for N, which is 24,000, and for Macalise it's like 4,000. So the number of values you need is almost the same in both cases, but the ratio of entries, because you have more chance to obtain a value when you have more rows. So you can success only in 5% of the collection of the syndrome entries. So that's why we wanted to say that even if you don't succeed on 95% to collect them, you can still find the syndrome, the correct solution to the syndrome problem.
I see.
The computation is always working. Even if you are done, you have more chance to do it.
Okay, then I have to ask you another question. The ratio of the syndrome entries here, it is a ratio, the ratio of known entries which might be faulty, or is it the ratio of?
So for instance, here, if you have 5% of all the ratio of the syndrome, so you have n minus k, so you have 12,000 entries, you just need 5% of the and make a
Pierre,
successful attack.
We're losing
10%.
Yeah, Pierre-Louis, you were interrupted by the connection at some point.
Sorry. So I said here, this value 0.10 means that you need 10% of the n minus k, which is 12,000 entries. So you need 10% of the 12,000.
Okay, but this is not noisy, right? So I need to know them exactly. Sorry, Pierre.
I think we are losing Pierre.
Yeah, but I think we were close to the end of the question, so maybe we can close it.
Pierre-Louis is back.
Actually, sorry. I thought I was. I can try again. Last time, maybe.
Okay.
The only question is 10% means 10% of not noisy entries we need to know.
No. 10% means if you have 10% of n minus k, so n minus k is 12,000. So if you have 1,200 entries which are correct with a noise, which is of this form. You see the color is,
yes.
The first is a binomial noise at t/4. So it's noisy values. If the noise is too big, you are screwed. But if the noise is not too big, you can successfully find the solution.
Okay, thank you very much.